In the previous recording on the topic which I'll now tell you is called magnetostatics, we discovered the existence of a new force that appears when we allow our source charges to move. And as I pointed out in the previous lecture, this is the first time that I've made an issue. I was going to say this is the first time we've allowed our source charges to move, but technically we allowed them to move when we were charging capacitors. But this is the first time that we've actually taken notice of one of the consequences of allowing charges to move other than just the fact that we move charge. Specifically, we found that when we allowed charge to flow through a couple of wires, that the two wires either repelled each other or were attracted to each other, depending on whether the current was flowing parallel in each of the wires, parallel to each other, or whether the currents were flowing anti-parallel, that is to say opposite directions to each other. If they were flowing anti-parallel to each other, up one wire and down the other, then the wires tended to repel each other. But if the currents were flowing parallel, both in the same direction, both up, both down, whichever, the wires actually attracted to each other. Again, the Coulomb repulsion force can't, or anyway, the Coulomb electric force cannot explain that result. Also, well, since the Coulomb force can't explain it, we have to look at the existence of a new, as yet undiscovered, or at least undiscussed force. And so it was also discovered accidentally that that wires with currents moving through them affected magnetic compass needles. And so we imagine the existence of what we will now have to call the magnetic force. It's going to turn out, so there's no point in delaying the inevitable, it's going to turn out that the magnetic force, like the electric force, is caused by and is related to a field. The electric force is related to an electric field, so too a magnetic force is related to a magnetic field. And just like there is a source for an electric field, and we call those source charges, so too there is a source for a magnetic field. And we're going to talk about what that is now. Okay. For historical reasons, which are far less interesting than you might think that they are, the symbol for the magnetic field, the symbol for electric field is capital E, which sounds really reasonable, E for electric, and that's true. The symbol for the magnetic field, though, is, well, it's not M, should be M, but it isn't. The symbol is capital B. And when I first heard of this, I wondered why capital B. And I assumed at first that it was related to perhaps the German word for magnetism or the German word for compass or something like that. And that turned out not to be the case at all. In fact, the story of where B, you know what? I'll let you look it up. But be prepared to be disappointed. In any case, wherever it came from, capital B is the symbol that we use to represent this magnetic field, whose properties we are now going to investigate. We're going to investigate them, reasonably enough, to start off with at least, through an analysis of the forces that this field creates. Some key points to start off with, key observations. All of these are results of experiments. First, I'm going to, by the way, talk about properties of the magnetic field, but I should be clear that most of these properties were discovered by observing the magnetic force that the fields create. And so we determine the nature of the magnetic field by observing its effects, notably, primarily the electric force. Okay. All right. This is perhaps the most important, or at least fundamental thing to know about magnetic fields. That only moving charges can create a magnetic field. Now, electric charges will create electric fields, of course. We know this very well. And the electric field of electric charges is created whether the charges are moving or not. Moving charges have electric fields. Stationary charges have electric fields. Okay, we're pretty good with electric fields at this point. We are going to come back to electric fields after a while, but we're going to do magnetic forces and fields for a while. But anyway, so electric fields have the electric fields exist. And electric charges create electric fields whether the charges are moving or not moving. But only moving charges can create a magnetic field. Okay, very, very important idea. An equivalent way to say this only an electric current can create a magnetic field. Okay. Second key point. The direction of the magnetic field vector, oh yeah, it's a vector also. Just like the electric field is a vector, so too it turns out the magnetic field is a vector field. And its direction, and this probably won't be terribly surprising, but it's worth mentioning anyway. The magnetic field's direction is dependent on the direction that the charges, the moving charges, are moving, or the direction that the current is flowing. Okay, so if a current flows one direction, the magnetic field vector that it creates will point a certain direction. If the current flows the opposite direction, the direction of the magnetic field changes also. And fortunately, the change is not random. It turns out that if you reverse the direction of the current flow, then you automatically end up just exactly reversing the direction of the magnetic field vector at that place in space. So it's at least it's a consistent relationship. So if the current is flowing this way, and so the magnetic field points, let's say, up towards the ceiling, then if the current flows this direction, then at the same location in space, the magnetic field will reverse direction and it'll point down towards the floor. Okay. If the current is flowing upward, then over here, so the current is flowing upward. Over here, the field, it turns out, the magnetic field vector will point this way. If the current is flowing this way, over here, the field is pointing out this way. What? This is all very confusing. Yeah. The direction of B is not simple. We got to talk about that. Okay. Third key point. This one is about the magnetic force now, not the field as such. And I want to emphasize As I said a few moments ago, the nature of the magnetic fields that a current creates was investigated by observing the effects of that field, notably the force that the magnetic field creates. Specifically, it's again found experimentally that if you have a magnetic field, a magnetic force can also exist. Doesn't have to, but can a magnetic force may exist where you have a magnetic field, but only if you'll only get a magnetic force. Even if you have a field, you'll only get a magnetic force on some other charge that is also moving. Okay, so if I have a magnetic field here in space, and if I take a test charge, let's say, capital Q, and I put it there in space, motion, initial velocity 0, and I let go of it, its velocity will remain 0. In other words, the magnetic field that I've just dumped the test charge motionless into, that magnetic field will have no effect, will apply no force on that motionless test charge. Okay? Magnetic fields only create forces on moving electric charges. So if I instead take my test charge and throw it through the field, then absolutely a force will come into existence, and we know a force exists because we'll watch the test charge accelerate. It'll change direction, or it'll speed up or slow down or whatever. Okay. So, and generalizing to not just one moving charge, but a whole collection of moving charges, in other words, an electric current, only electric currents can be affected by a magnetic field. And so a nice summary way to say this is, it takes a current to create a magnetic field, and it takes a second current to be affected by a magnetic field. Okay? Magnetic field, and the key concept, the key idea is that only moving charges will experience magnetic forces. Motionless charges cannot and do not. And so it takes a current to create a magnetic field, and it takes a different current to be affected by a magnetic field. All right. So those are some general observations. Now I want to start developing a way of calculating this magnetic force. And then once we've got the magnetic force under our belts, then we'll shift to the next question, which is how do you calculate the magnetic field? So let's do that. We will start the process of understanding the magnetic force and coming up with a mathematical expression that describes it by choosing the simplest possible situation, which is a single moving point test charge in a magnetic field created by some source current. And I'm going to come back to this point later and make a bigger deal out of it, but for now, you should keep in the middle of your minds that we have in magnetostatics the same kind of concept that we have in electrostatics, which is the concept of a source and a test. Remember, a source charge is the source of the electric field. The test charge is the thing that experienced a force if you put it in that field. We're going to have the same thing, or similar kind of thing, in magnetostatics. We're going to have a source current, source of the magnetic field, and we will have a test current, the current that is experiencing the force if you put it through the magnetic field. And finally, well, no, I'll save that for later. All right, so let me draw a source current and a test current. All right, first of all, I should point out that a couple of things. First of all, I am going to do the same kind of thing I did with electrostatics, which is I'm going to start with the simplest possible physical situation I can come up with that will show the effects that I want to show. The problem is that the simplest possible arrangement for electrostatics and electric fields was a single point charge that was just there floating in space. But that option is not open to me with magnetostatics because a motionless charge doesn't create a magnetic field. And so my charge, I have to have a continuous train of a bunch of charges all moving from the very beginning. And so both the physical arguments and the mathematics are going to be much more, well, noticeably more cumbersome than the arguments were for electrostatics. But that's okay. You're comfortable now with the mathematics. We're going to take the next step. So you're there. You're ready to do this. So no worries there. The next thing, well, I should say this, and therefore the simplest possible arrangement that I can come up with that will create a magnetic field, and the simplest magnetic field that I can create is the magnetic field of an infinitely long straight wire carrying a constant current. Constant, by constant, I mean constant in time. And constant in time current, that's why we call it magnetostatics. When we allow the current to vary with time, we'll get into magnetodynamics. Okay. Finally, we are going to, unless I explicitly say otherwise, all of our source currents are going to be created by moving positive charges. There's a reason for that choice, which I'll describe in a future lecture. But the direction that the current flows is arbitrary, and I can change it from problem to problem, and I will. But let's suppose that the current is flowing like this. Okay. Then what we will do is, okay, so there's a magnetic field created by this current. We know nothing about it other than what we can gain, what we can glean from observing the force that it creates on some other moving object. I'm going to have a test current. In this case, my test current is going to be not another wire, although that will be my second example. No, my first example is going to be just a single moving point charge, Q. Now, this sounds like it might be contradicting what I said a moment ago, that you can't have, that a long straight wire carrying a constant current is the simplest arrangement that I can come up with for a magnetic field. And I stand by that statement. A moving point charge, although I can, and I am about to calculate the force on it, it would not be a good source for a magnetic field. The reason is, it is true, and we'll discuss this later in a few weeks, it is true that this charge, since it is moving, it also creates a magnetic field. However, that magnetic field is temporary. It is highly time dependent. Basically, the charge carries its magnetic field with it, and it's here one moment and gone the next, and I don't have a magnetic field a millisecond later. So it's not a terribly useful field. So the simplest possible useful magnetic field is from a long straight wire. Okay, so we do this. So we fire this positive test charge from nearby this wire, and we will assume that they are a distance d from each other. D is d what I want. Z. It doesn't really matter at this point. Stick with d. Okay. Distance d apart. Okay. Question: what happens? All right. Well, if you were paying close attention to the previous analyses, then you'll see that this is superficially similar to the two currents that were flowing parallel to each other from the battery, and those two wires attracted each other, and so you might guess that there will be a force of attraction here, and if you guess that, you're correct. So there's a force of attraction. Now there's a force on the wire as well, but I'm going to ignore it because I'm interested in the force on the charge, not the force on the wire. All right, so force on the wire points like that, and V points like that. On the other hand, if I were to put the positive charge over on this side, now this is where it gets peculiar. So watch this. In one sense, it's not peculiar at all. If my charge is moving this way, then again, you expect the charge to be attracted to the wire, and it is. And so the force on it would point this way. Okay. But if you think about it for a moment, that's awfully peculiar, because how does the charge know which side of the wire it's on? And in fact, I will tell you this much: if our test charge were out here in front of the wire, out here in space, the force on it is again going to be attractive towards the wire. It's going to point this way. If the charge were behind the board, still moving upward, the force on it would point this way. Okay, so it's going to take a very peculiar. And by the way, this was the sort of thing I was talking about, where I said that I slightly misled you in the previous conversation when I was talking about the compass needle pointing different directions. I didn't actually lie to you. It's just that the forces on a compass needle work differently than the force on a moving test charge, and because a compass needle just works differently than a charge. So, but what I'm telling you here is quite correct, and this is really what you should focus on. All right, well, I've got V going this way. In other words, the current, if you will, is flowing this way. The force is pointing everywhere towards the wire. It's going to take an awfully peculiar magnetic force and an awfully peculiar mathematical relationship to explain this away. And our hint as to what's going on, I still haven't put the magnetic field in here, but we're going to draw off the experience of the compass that I described in the previous recording, and guess that the magnetic field now that the wire is creating, and the magnetic field, therefore, that is affecting this moving charge, that magnetic field does not point towards the wire. It doesn't point away from the wire, but rather, like the compass needle suggested, the magnetic field circles around the wire. Okay. Specifically, the magnetic field, which I will draw in red, just because why not, over here, we will find that the magnetic field points into the board. Over here, we will find the magnetic field points out of the board. Out front, the magnetic field points this way. Behind the board, the magnetic field points this way. And if I were to draw this picture on end, so this is now my wire with the current flowing, let's rotate it this way. So the current flowing into the board, so this is the current, okay? We are going to guess that the magnetic field, like I said, it circles around the wire. Now, how I decided that direction, I haven't said yet, but I'll explain it later. And this is a guess that we're making right now. Now, these are field lines in the same sense that we have electric field lines. And these are all perfectly concentric on the flowing current. Okay? So this is the stuff in red is the magnetic field. And in this example, our charge is moving parallel to the current flow. And so our charge, and I know this is getting confusing, there's Q, flowing, I'm sorry, that's Q, and it's velocity vectors, what I should be drawing here. Velocity pointing that way. Okay, so we have the velocity pointing into the board. We have the magnetic field is our guess, is pointing around, and so what this means is at this specific location, for example, the magnetic field, like the electric fields, by the way, the electric field is pointing right here, is pointing tangent, so it's pointing straight down. So this here is the magnetic field vector. All these, and these red circles are the magnetic field lines. Exactly the same distinction that we were making between electric field vectors and electric field lines. And so we have, okay, the magnetic field pointing down, the velocity pointing in, and the resulting force pointing towards the wire. And now that drawing has gotten impossible to understand, so let me pull out the relevant vectors here. We have the velocity vector pointing into the board. We have the magnetic field vector pointing this direction. We have the force vector pointing that direction. Okay? All right. And the thing that's moving is our charge Q. So B is created by the source current, the thing in the infinitely long straight wire. V is the instantaneous velocity of our positive test charge, and F is the direction of the force that it's experiencing. What we want to do now is come up with a mathematical expression that relates these observed physical facts. And between now and starting the next recording, you should take a few moments and try to think of what mathematical properties must the function that describes this force have? What mathematical properties must the force function have for all this to work? And I will give you a hint. It's something that you saw in the last couple of weeks or so of mechanics. We'll go to the next recording.